Good morning. Welcome to the course on partial differential equations, or to be more precise, a course in Fourier series and boundary value problems, because as we will often discuss in this class, you will see that the topic of partial differential equations is extremely vast. All of you who take this class, or usually those of you who take this class, also took a class in ordinary differential equations, which is also a very large subject area. Even so, comparatively speaking, you could cover quite a lot in a year-long or a semester-long course in ordinary differential equations. In particular, if you took the ordinary differential equations course with me, you basically covered the entire method of solutions for linear equations and systems, which is a nice topic, or Laplace transforms. So many topics, many methods of solving a large class of differential equations, and so on and so forth. So by the nature of the mathematics of partial differential equations, you will see that things are much more widespread in terms of the types of equations that came to be, and to make matters even more complex, the same type of equation can require completely different mathematical tools, even if we change the problem just slightly. So just to anticipate a little bit, to see, like they say in movies, to have a preview of coming attraction, so to speak. Just as an example, in many cases, for instance, whether we use Cartesian coordinates for the functions that we try to find versus, let's say, spherical coordinates, which is often a necessity in many problems, right? So depending on the shape of the objects that we want to analyze, for example, when we will talk about the heat equation, for instance, right? So you have objects that are heated and you want to track the temperature of the object at various points on the object. Whether you use Cartesian coordinates to represent that object versus spherical coordinates entails using a completely different set of tools. Let's leave it vague like that for now. A completely different set of tools, which basically will require in turns maybe a chapter to learn in order to deal with those. So this is not to actually put a damper on the mood in the beginning, but just to anticipate why this subject is so vast, and why we basically cannot really cover the same type of generality that we could cover in ordinary differential equations. But this is also the same reason why the topic, in my opinion, is very interesting, right? I mean, changing just a little bit on the problem leading to a completely different set of tools to handle that problem is what makes the class quite interesting. But I'm mentioning this in the beginning because I want to make it clear from the onset what we actually are looking for in this class. What is the actual goal when we say we study partial differential equations? So that means what is the precise subset of equations or methods we're going to deal with, so that you don't have a wrong expectation, so to speak. And that's why I like in this class to take my time with the introductory part. In fact, depending on how much time I'm going to use right now in this first lesson, there will be probably either a slightly longer or maybe two different introductory lectures. So let's actually write a definition, a very general definition, and some notations. And then we're going to continue with some examples. And the main purpose for this first set of examples is to just make a distinction between, or to point some differences between ordinary differential equations that all of you taking this class should know something about, and partial differential equations. So just for a definition, we could say that a partial differential equation or abbreviated a PDE, is any equation in an unknown containing, so is any equation that contains an unknown function of two or more variables and sum of its partial derivatives. So a very general definition indeed. Now it has to be about functions of two or more variables because that's what makes it different than ordinary differential equations. So just to remind you, an ODE, so an ordinary differential equation, or an ODE, basically is the same definition except we are dealing there with functions of one variable and their derivatives. So in the case of a differential equation on ODE, you typically have an independent variable, let's say t, denoting usually the time, and then a function y of t, and then of course the equation contains y prime, y double prime, and so on, various derivatives of that function in the equation itself. In the case of a PDE, like I said, we have a function of two different variables. So let's establish a couple of notations for the partial derivatives. And then a quick example, just a refresher on how you take partial derivatives. So let's say we have a function of n variables. Let's say u is a function of n variables, x1, x2, xn. So you could write u of x1, x2 up to xn. So then we have basically two different types of notations for the partial derivative. So the partial derivative of u with respect to xi, you can denote it using the del operator, del u, the partial u, partial operator, partial u, partial xi, or as it's more convenient, often u sub xi. I'm going to use the index notation more often because it's more convenient. So the partial operator is usually when you want to take a partial derivative without naming the function. So let's take a quick example to actually compute a partial derivative. So let's say you have a function of two variables, u of xy equals x squared plus xy plus y squared. So partial x, which you can denote it by partial u, partial x, or u sub x, that's going to be 2x plus y. Partial y, if we use just the index notation, that's going to be x plus 2y. You could also have, of course, higher order partial derivatives. So one confusing part sometimes with the partial operator is that it adds the operator, partial operator is from left to right and the index from right to left when you take the second order partial derivative. So for instance, the second order derivative with respect to x and y looks like that, and in the index notation that's going to be written like this, so u sub xy. This is because The idea is that if you use the partial operator, let's say I want to take partial x first and then partial y first of this expression. So you do partial with respect to x of the expression x squared plus xy plus y squared. And then if I want later to do partial y, I add that operator to the left of the original one. So we don't use this too often, but this is to point out that if we don't name the function, so if I don't name it like I did it here, u of xy, the partial operator is used to indicate which partial derivative you do each time, right? So if I do partial x first, that's going to be, like I said before, 2x plus y. And then you do partial y again, and that's going to be, of course, 0 plus 1, right? Because x is a constant with respect to 1. And so that's going to be 1. If we use the index notation, it's starting with the index closest to the variable, right? So u x y, that means u partial x and then the answer partial y. Okay, so u partial x again is going to be 2x plus y, and then partial y again, which is 1. So we're not going to use this too often, but if you see it in the book or in many other applications, again, if we use the partial operator, the order of differentiation is from right to left, as indicated here at the denominator, at this symbolic denominator. Partial x first and then partial y. Using the index notation is from left to right, starting with the variable closest to the function itself. Because we solve differential equations in an unknown function u, which will appear in the equation itself, we're not going to deal too often with the partial notation. So we're going to prefer, for the most part, the index notation for the partial derivative. So I hope it's clear. Make sure you ask during office hours if there are any issues with the notation and what constitutes a PDE. And then in the next part of today's lecture, let's go over a couple of basic differences between differential equations, ODEs, ordinary differential equations, and PDEs, with very simple examples, but extremely important just to understand the motivation actually for what we're going to do later in the course. So stay tuned for the second part. Okay, so let's talk about a couple of examples and then analyze some important differences between an ODE and a PDE. So let's start with an example of an ordinary differential equation, which you probably talked about in the class of ordinary differential equations that you took before. So let's say you have the famous mass spring system without damping. Now, if you don't remember all the details at this point, you don't need to pause the video and go back to refresh yourself on the ODE system and mass spring systems, because I'm going to focus just on the mathematical aspects, but I just want to compare essentially two word problems between the ODEs and the PDEs. So in the mass spring system, if you remember, you have an equation which describes the motion of an object attached to a spring. So for example, let's say you have a spring here and an object of a certain mass, and then the spring can oscillate left and right, and then the equation gives you essentially the displacement of the object. And if there is no damping, a typical equation of the mass spring system contains the second derivative and y itself, right? So I mean, let's say y of t is a displacement of the object at time t. And so suppose that the equation of motion for this object is y double prime plus y equals 0. That'll be basically an object of mass 1 and spring constant also equal to 1. The middle term, y prime, the one with y prime, which is missing here, would be the damping. But if I say no damping, then that means it's equal to 0. So, oh, and I forgot to mention, although you should probably remember this from ordinary differential equations, that for simplicity, we don't write y double prime of t or y of t, right? We just use shortcuts. We don't mention of t, the argument, all the time just for convenience. So when we say y double prime and so on, we really mean y of t, y double prime of t, and so on and so forth. And I should mention here that the same convention works on PDEs, right? So I mean, for example, if I have a function of two variables u of x, y, I don't need to write u of x, y all the time. If I take partial x, I don't need to write partial x of x, y, and so on. We can simply write u partial x, partial y, and however many partial derivatives we need in that problem. And by the way, this convention is even more useful, obviously, in the case of partial differential equations, because it will be really tedious to write so many parentheses if we don't need to. So we're not going to get into the details how we solve this. Let's take for granted that the solution, the general solution of this equation, of this mass spring system, is going to be y of t. I'm going to write now of t just to write it as a solution, as a full function here. Some constant cosine of t plus some other constant sine of t. And that'll be the general solution. Now, here's an important question that I want to address here, and I want to ponder here, and remember this question when we move on to an example related to PDEs. If I basically want to ask, what is the displacement at time t equals, I don't know, let's say 10 seconds or 10 minutes, depending on the time unit measure. We don't know the answer just from the general solution, right? I mean, we just know that the displacement will be obviously c1 cosine of 10 plus c2 sine of 10. But really think in terms of practical matters. Let's say you are running an experiment. I mean, you're doing this equation for a purpose. You actually have a device, a mass spring system, and you set up this differential equation for the purpose of asking precise questions like this, you know, what's the displacement at a certain time t? So you know already the answer, well, you know the answer why you cannot give it the answer in that format, because we don't know actually what is that displacement. You know, these general solutions seem to be in terms of arbitrary constants. And if they are arbitrary constants, that means without any extra piece of information, we don't know what that solution is after all. Now, of course, we know a great deal, and let's keep that in mind. We know a great deal about the solution, namely that it seems to be a combination of cosine and sine, yet we don't really know what it is unless we know something else about the experiment. And if you think about in real life, we always know more than just the equation of motion, because that object that you started with here, you know it has some initial displacement. It has, I mean, you know something about the object. If you don't know anything about the object, you basically are left with this generic solution, which doesn't give you the precise answer to your question. But in practice, like I said, when you run this experiment, you have some initial piece of information, which of course, in the course of differential equations, you call that initial conditions. So initial conditions meant that when time is equal to 0, I can know, or if I know what happens at the time equal to 0, like the initial displacement, let's say the initial displacement is equal to 1, and then the initial velocity, which is y prime of 0, is equal to minus 1. So initial displacement and velocity. And if you have sufficient initial information, and by the way, from the physics, you know exactly how much information you need. So to determine a motion in the context of a mass spring system, you need both the initial displacement and the initial velocity. so that you can determine exactly what goes on, what the solution is to the motion. And of course, we can quickly find C1 and C2. We could do this just for fun. So y of 0 equals 1. That means C1 cosine of 0 plus C2 sine of 0 equals 1. We need y prime of t first before I plug in 0. Minus C1 sine of t plus C2 cosine of t. And then y prime of 0 will be minus C1 sine of 0 plus C2 cosine of 0 equals minus 1. So sine of 0 is 0, cosine of 0 is 1, so that gives me C1 equals 1 and C2 equals minus 1. So if I give the initial conditions, the solution of the problem is cosine of t minus sine of t. All right, so let's keep this in mind. The remark that I want to make before we move on to a simple PDE usually the important thing is not so much finding the general solution, but finding the solution that fits the initial conditions. Because in practice, you basically want to solve an experiment, so you want some precise answer as to what happens in the future. Now, of course, because in the case of differential equations, we could find general solution for a large class of functions. It's still a huge thing to be able to find the general solution, because usually after that it's a formality in terms of finding the particular, finding the solution that fits the initial condition. In this case, it's just solving a simple system. But as you will see in the case of PDEs, things are a little bit flipped in the sense that not only it's far more important to fit some what we're going to call boundary conditions later, but that's where the big problem lies, mathematically speaking, as well. And whether we finding the general solution, it's sometimes, even if we could find it, now first of all, most of the time we cannot find the general solution, but even if we could find it, it is really not that useful without fitting some extra pieces of information about the experiments, the so-called boundary conditions, as you will see in the next part of the class in a minute. So on the next page, I'm going to write down a very, very simple PDE, and I think that'll be enough for this introductory lecture. And then we're going to have another introductory lecture, just let's call it introduction part 2 later on. So stay tuned. Okay, so let's finish an example with a simple PDE. In fact, this PDE example that I start with is so simple, it will be basically almost disappointing, but it will still serve my purpose. And again, be patient. For those of you who take this class with me, one of the best skills to come up with as soon as possible in this class is to really be patient, because everything has a purpose. You'll see later. It will be a little bit frustrating, I should say, in the sense that it will be quite a while, a couple of weeks at least, until we actually get to learn about the main method of solving a PDE, the method that we're going to deal with in this class. But these little remarks that I'm going to go over in the beginning, trust me, will serve a purpose. And this first example, like I said, it will be nearly disappointing in its simplicity, but it will, I hope, make the point to motivate actually what we're going to deal with later in the class. So, like I said, let's consider a word problem, right, to motivate this example, just like before. So in the previous page, we had the mass spring system. In this example, we're going to consider basically what we're going to call later a heat equation, but a very simple form of it. So consider a thin metal rod of length L. Now imagine basically a piece of metal here, a rod of negligible thickness, essentially. That's what I mean by a thin. In the sense that the material essentially is just identified by the x coordinate. I mean, if you imagine that this is basically in the Cartesian coordinate, this metal rod aligned from the origin to the right, basically each part of the rod is identified by its x coordinate, right? So you have the left, so basically x equals 0 is going to be the left end point, or the end side, and the x equals big L, the right end point. And let's denote, and pay attention here, let's denote by u of x t, little t, the temperature of the rod at time t and location x. Okay, so obviously we justify the existence of partial differential equations, meaning that the temperature is not the same along the rod. If it was the same, of course, you would need only single differential equation, I mean ordinary differential equations. So whatever we deal with in this class when we talk about PDE are applications for which we need at least two variables. Usually one of the variables is the time. That's still the case, not always, but it's still the case that one of the variables is the time, because most applications look at dynamical systems, stuff that change in time. But they also depend on something else, usually a spatial coordinate, in this case the x coordinate. Okay, so that's the temperature of the rod. And let's say the statement of the problem that we want to model is that let's say that the temperature of the rod does not change in time anymore. So that means, let's say it reached a thermal equilibrium. Now notice that's not to say that the temperature is the same on each location. We just basically say that at some point in time, because of some magic or some conditions that I impose outside around the rod, I mean, imagine there are little devices around the rod that at some basically add or remove the exchange of the temperature with the external medium, so that, you know, in time along the rod there is no change in temperature. So there are some heating or cooling devices that will basically keep everything in check so that the temperature doesn't change anymore. This is also called the steady state temperature. We'll get to that later. But if this is all I'm telling you, that this temperature doesn't change in time, if that's all you have, and you want to basically, and the question is basically to write a PDE describing this phenomenon, then all you could say is that the derivative of u with respect to t is equal to 0. So the derivative of u with respect to t at xt is equal to 0. Now remember the convention, let's get used to that already. We don't write off xt all the time if there is no risk of confusion. So really that's all there is to it. I mean, if all I say is that the temperature doesn't change in time, then all I could say in terms of a PDE that describes this this phenomenon is that u partial t is equal to 0. Right? So no change in time. It means that the derivative with respect to the time t is equal to 0. So that seems a very simple ODE, PDE, and it is very simple indeed. But here's the general solution. And I'm not sure how many of you can pause, maybe you can pause the video a little bit and try to think what could a solution look like if you think about. When you see a derivative equal to 0, many of you maybe think in terms of that should be a constant, right? I mean, we know that from single variable functions, if the derivative is equal to 0, that for any time or any variable, that means the function is a constant. But keep in mind, my function here is of two variables, not a single variable. So as it turns out, the general solution is really any function of x. Because if you think about, there's no reason to restrict our function here of just a constant, right? I mean, forget about the physics a little bit, right? If I just tell you that a partial derivative with respect to one variable is 0, all we know is that u of xt should be constant with respect to t, but not with respect to x. There's no reason to assume that the function is constant with respect to x, so that means it can be really any function of x. So this is one of the most important remarks that we should write it down. Basically, general solutions of PDEs depend on arbitrary functions, not just constants. And here where lies all the beauty and the complexity, in fact. And this will be basically my starting point of justifying some of the things later when we move on to the second introductory lecture. But I want you to close the books on this lecture for today with this main difference, right? We had before a ordinary differential equation, and then the general solution was not specified, right? It was unsatisfactory in the sense that we didn't have a precise solution, but it depended on arbitrary constants. So we still had quite a lot in terms of a solution, in terms of a function there. All we had were just some initial conditions, and then we could find those constants. But as it turns out, if we just solve a PDE, if we're lucky to find the general solution for a PDE, that solution depends on arbitrary functions. And so it still now begs the question, how can we answer the question that we may have later in the problem? For instance, at a later time t, what is the precise temperature of the object? Such solutions in form of arbitrary functions are not going to be useful ever, right? Because again, presumably you do these problems for answering specific questions. In this case, the temperature of the object at a certain location at a certain time t in the future. So, and now in terms of what is the extra information that you need to find these arbitrary functions, well, we're going to have to talk about more on the next lecture, but suffices to say is not just basically an point in time, an initial condition. Now, for this problem with the metal rod, you kind of guess a little bit that I should probably know the temperature in the beginning at all location, right? So I mean, I should probably know something like this, right? So I mean, when time t equals 0, what is the temperature at each location? But you will see later that the variety of these initial pieces of information is quite vast in terms of partial differential equations. There's far more variety in terms of what type of initial conditions or boundary conditions, as you will see later. We'll talk about later on the difference between initial conditions and boundary conditions. And to make matters even more interesting or complex, it's not even always simple or clear what are strictly the necessary boundary conditions or initial conditions you need to have so that you can end up with a unique solution that will determine the function that you're looking for. Now, from physics, we often can figure out what those conditions should be because we understand the physics of the phenomenon. But if that's not completely understood, then the question of what those initial conditions should be or boundary conditions, it's complex in itself. So in other words, it could be a difficult problem even writing it down completely in both the equation and the necessary conditions to begin with. So I think that's enough for our first lecture. We'll see you next time.